All right, so questions before we just kind of go through a review. Any particulars up front?
Are you going to have any mathematical induction problems in which you have to use strong mathematical induction?
I don't think so. Strong induction is really just saying assume P of n for all n
All n up to that.
up to
Yeah.
some given n, and then prove it for n plus 1. And those are usually easier to do because you've got more things you can assume.
Is there a list of subjects that will be covered on the
Yeah.
examiners and listeners? What we can do over there?
So there's a final exam study guide. So the italicized things in brackets I'm not going to ask you about because we didn't go over them, or we didn't go over them in the detail that I would like for asking questions on them. Or grammars and languages, we went through all of that, but we didn't have a homework on it because it was the last week, so I won't ask you about those. So if there's no questions, I'm just going to run through this from the start and talk about it.
Again, the recursive function problems, it's like I was acting in class. Are you going to have problems on the test that ask us to come up with the recursive relationship?
No.
Okay.
But I could have something like, this is not an exam question, but I could ask a question like this, right? I can define f of n recursively as n plus f of n minus 1. If n is bigger than or equal to 2, it's equal to 10 if n is equal to 1. And I could say find f of 5. And so it's applying that definition.
Would you have a problem that gives us a recursive relationship and asks us to find a closed relationship?
No. Like find a formula for f in terms of n. No, I won't do that. But if you wanted to do this by hand, right, the easiest way is to go forward. Start with f of 1. Well, we know that's 10 because we're told f of n is 10 if n is equal to 1. And then use this definition. F of 2 should be 2 plus f of 1. And we already know what f of 1 is, so this is 2 plus 10, which is 12. F of 3 should be 3 plus f of 2, which is 3 plus 12, which is 15, and so on. So just kind of understanding that, you know, we can define a function in terms of itself like that.
And you wouldn't do that and ask us what f of 100 is?
I probably would not unless there was a really clear way to answer that. I won't, but I could ask you to find g of 100 here. So g of 1 is 1, and g of n is negative g of n minus 1 for n bigger than 1. So if you start trying to do this, g of 1 is 1. G of 2 would be negative g of 1, which is minus 1. G of 3 would be negative g of 2, well that's negative minus 1, so that's 1. G of 4 would be negative 1.
Gosh, there's a pattern there.
And there's a pattern there. So you can figure out what g of 100 is. And again, CSE 222, right? Recursion is a big part of that course. and the topics we cover in there. So writing functions in terms of themselves will be something we do a lot of. And so this is just, you know, another introduction to that concept. All right, so sets, right? Sets, loosely speaking, are collections of things. And if we're not very careful about how we define a set, we can get into paradoxes. But for this class, we just think of a set as a collection of things. And there's no such thing as a set that contains two of the same thing, right? It's a collection of unique things. And so we can define the set by looking at things and saying, is this in the set or not? Right, in the collection of things that are in the set, that's the set. We can talk about the size of a set. If it's finite, it's the number of things in the set. It's what we think of the size as being. For infinite sets, the size gets harder, but I won't ask you questions about infinite sets as far as cardinality. We can do operations on sets, so we can take unions, we can take intersections, we can take complements. We can subtract one set from another. That's the complement of a set. We have Venn diagrams, which are a visual way of representing sets and intersections and unions and so on. There's the universal set, which is the collection of all possible things that could be in any set that we might talk about. So if we're talking about sets of integers, the universe would probably be the set of all integers. And we might have a set containing, you know, the numbers 2 and 7, or containing the positive integers or the primes or whatever. And we have some typical sets. Z is a set of integers, Q are the rationals, R are the real numbers, C are the complex numbers. N are the natural numbers, which may or may not include 0. If I don't tell you, ask. But they're the numbers that appear in nature, apparently. Subsets are, you know, sets that are made up of elements of another set. So if we have the set of even integers, we could have a subset which is the integers that are multiples of 10. And we know that all of those are going to be even, but that's not all evens. The power set is the collection of all subsets. So the power set is a set itself whose elements are the subsets of your original set. And those get big really quickly. Cartesian products are a way to combine two sets to create a new set, and this is where we talked about tuples. So if you have a set like you know, 1 comma 2 and b equals x comma y, then we can take the Cartesian product and it's a set of tuples. Where the first thing comes from A and the second thing comes from B. And so the Cartesian product here would have 4 elements, which are these 4 ordered pairs, right? First thing comes from A, second thing comes from B. And the maybe go-to for that is Cartesian products, as in taking intervals and getting Cartesian coordinates out. So if you take the set of real numbers, Cartesian product with the set of real numbers, you get sets of pairs of real numbers. Those are like coordinates on a graph, x and y values. We learned about a bunch of set identities, and these are in ways similar to stuff from Engineering 250. So A union B equals B union A. A intersect B equals B intersect A. A union A equals A. We have an empty set that's a set containing nothing. A union the empty set equals A. A intersect the empty set equals the empty set. And so on.
On the purple sheet.
There may be some of this on the purple sheet in the language of logic, but it's the same stuff, right? Yeah, and bring your purple sheet with you, and it doesn't count against your your 4 pages of notes. So there's these set identities, including De Morgan's. And distribution, and so on. There's De Morgan, one form. All right, functions are basically maps from one set to another set. So if we have a function from A to B, we can write something like f is the function colon A arrow B. And it means for each element in A, f gives us an element in B. And we could define this by simply saying what f of every element in A is. So maybe f of 1 is equal to y, and maybe f of 2 is also equal to y. All right, so that's a function. I could take 1 to x and 2 to y, that's a different function. But we can define this function by simply listing what it does to each element in this first set. So this is called the domain. This is called the codomain. And we talked about injective, surjective, bijective, but we didn't talk about them a lot. And they are really confusing to most people, so I decided not to put those on the test, so don't worry about them. But you should know what it means for a function to be well defined. So this is a perfectly valid function, even though nothing's mapping to x, that's okay. That gets into being not surjective, right? And 2 different values both go to y, well that's totally fine too, that's just not injective, okay? But if I also said, you know, f of 1 is also equal to x as well as y, that's no longer a function, okay? Each value in A has to go to only one value in B. Different values can go to that same value in B, but one cannot go to both x and y. Okay, it's not a function. In the sense that if someone says, hey, what is f of 1 equal to? You can't answer it. You can't say it's x or it's y, you'd have to say it's both, and that's just not what we mean when we talk about functions. So there has to be a unique mapping for each element from A. And this is the vertical line test in like a pre-calc class. All right, we talked about summations. So summations are basically for loops. Sum from I equals 0 to 10 is like a for loop for I equals 0, I less than or equal to 10. And the thing that you're summing is the body of the for loop. So figure out what that thing is in, you know, the body of the summation symbol for each of those values of I, and then just add them all together.
Will we be doing double summations?
And you might do double summations, which is really just so sum from I equals A to B, sum from J equals C to D of some function of something. Just think of it as a single summation, right? First, figure out what this is, right? That's just a plain old summation. Whatever you get for that, you know, if this turns out to be equal to squiggly line, then this whole thing is just sum of squiggly line. So just start with the innermost summation, figure out what that is, and work your way outwards. And double summation is a nested for loop. And if you see one of these, that's a product. It's just like a summation, but instead of adding all of these together, you multiply them. And that's also a for loop, except you're multiplying a running product in the inside of your loop. We talked about matrices. I will not put matrices on the test. You'll do matrices in CSE 215 or in Math 215. So I wanted you to see them, but I won't test you on them. Propositional logic. All right, I need my purple. have the special non-purple sheet. So these look a lot like 250, they look a lot like set theory. We have these identities and these rules that we can use when we're talking about logical operations. Let me back up first. Propositions, right? Make sure you know what a proposition is. It's a declarative statement that has a truth value. So x is not a proposition. If it's a variable, x times 2 is not a proposition. X times 2 is bigger than y, that is a proposition. Okay. And so if we have a set of these declarative statements, we can combine them to make new propositions or modify them to make new propositions. So we can take two propositions and take their conjunction, that's an and. And we get a new proposition saying this first thing is true and the second thing is true. And that's a declarative statement with a truth value. We can do a disjunction, which is an or. So P is true or Q is true. We can do negation. So if P is a proposition, then not P is another proposition. P is the proposition that today is Friday, not P is the proposition that today is not Friday. They're both declarative statements, so they're propositions. And so there's these identities, right? P or Q is the same as Q or P. P or 0 is the same as P. P and 1 is the same as P. And, you know, A union, the empty set is A. A ANDed with the empty set is the empty set. P ANDed with 0 is 0, right? So these are analogs to those.
So are we only going to use those like in the context of proofs, or we're going to have kind of more standards?
I could ask you to verify these with a truth table, with a membership table, for sets or, you know, things like that. But mostly you want to know these for proofs. That's the real more practical part for this course. So there's De Morgan, there's double negation, so on and so forth. So inference, right? So this is the if-thens. So assuming everything in sight is a proposition, then this is another proposition. If P, then Q. Right. If today is Friday, then X is equal to 12. That's a proposition. And we write it as P arrow Q, and we read it as if P, then Q. And our understanding is that this implication, this bigger proposition, is always true unless P is true and Q happens to be false. So if today is Friday, then X equals 12. Well, if it turns out that today is Friday and X is not equal to 12, then this if-then statement is false. Because it says if P, then Q, and if P is true and Q is not true, this is clearly false. But that's the only case in which this is false. Which means if P is false, this is still a true proposition. So the if false, then anything kind of thing. And so we can do proofs, which are really big, long strings of inferences. Prove that if x is an even number, then x squared is even. I mean, that's an if-then statement, right? And we can prove an implication by saying, right, we want to prove if A, then Z, where maybe A is the proposition X is even, and Z is the proposition X squared is even. So we're trying to prove A implies Z. And what do? We basically start off with A, which we're taking as a hypothesis, and then we write down something that follows from A. Well, what we're really doing is we're stating that if A is true, then B is true. And then we're stating if B is true, then something else is true. And we can continue with this and eventually show that something that we've shown is true implies Z. And then we're basically saying, you know, therefore, if A, then Z. So when we write out a proof, we're really doing a bunch of implications, using these different things like detachment and disjunctive addition and conjunctive simplification and all of that sort of business. But remember, when you're doing this, everything you write is a proposition, and everything you write has to be true. And it can be true because you're assuming it's true, or because it follows from something else that's true and some law of logic that says, you know, if these conditions are true, then this other thing is true. Right? But everything's got to have a reason for being written in the proof. And if you write something that's not true, you can say, let's assume this, that's okay. But you got to remember that that's an assumption, so everything that comes after that is also an assumption. And usually when we're doing that, we're trying to work our way to a contradiction and say, therefore, we could not have assumed that, right? That assumption must be wrong. If we assume something, it's very hard to conclude that anything else is true after that. Assume x equals 7. Well, then I can say x squared is equal to 49, and then I can say x squared is less than 50, and I can say all kinds of things, but I don't know if any of that stuff is true unless I know that x is equal to 7. So if I'm trying to prove x equals 7, right, maybe I can find a contradiction and say, well, x can't be equal to 7, but I can't prove it by assuming it's true. And this is not obvious stuff, right? You know who Copernicus was?
Studied the stars. And
Study the stars and the motion of heavenly bodies, and had this theory that the sun was the center of the solar system, not the Earth. And by taking measurements of where the planets were at different times of the year, he constructed a model for how these planets would move if the Earth was the center of the solar system. The Earth was supposed to be the center of the universe at the time, and so it would be the center of the solar system, and he constructed what the paths of these planets in space would look like. And they were all twisty and turny and wobbly and stuff like that. And then if you put the sun at the center of the solar system, you got these nice elliptical orbits. And he concluded, you know, the sun is at the center of the solar system, not the Earth. And that was heresy, right? That went against church teachings. And Copernicus is remembered most not for figuring out that the sun was the center of the solar system, but for how he did that. And the way he did that is what we call the scientific method, which was to have a hypothesis, design an experiment, run the experiment, collect data, analyze the data, and then see if it supports or denies the hypothesis. And when he did this, and he, you know, claimed to have shown that the sun was the center of the solar system, nobody got too worked up over it. Even though such an idea was heresy, because they didn't think he had done anything valid, because he started off by assuming the sun was the center of the solar system, and then collecting data and building this model and seeing where he led to. And the wisdom at the time said, well, you started off with, you know, an assumption that we all know is false, so everything else that you've done is meaningless, you know. So people mostly ignored his work at the time. So this idea of being able to start with something right? And then argue logically from that and have all this stuff be true if that's true, right? That's not an obvious thing, right? It was not obvious back in his age, and it may not be obvious to us today. But that's what we basically do, right? We have a hypothesis and we say, if that's true, then these other things also follow from it. All right, so logical equivalence, right? So we can have propositions that are equivalent to each other, meaning they have the same truth value in all cases. So for example, if P and Q are propositions, this is the proposition that P and Q are both true. This is a proposition that Q and P are both true. These are logically equivalent. They have the same truth value in all cases. If it's sunny, then I'm running. If I'm running, then it's sunny. Or sorry, if it's sunny and I'm running and it's sunny, right? Depending on whether or not it's sunny and whether or not I'm running, these will have the same truth value as each other. So these equivalences, these double arrows that we see, if P, then Q is logically equivalent to not Q. If not Q, then not P, right? Those two propositions on either side of that double arrow always have the same truth value. And you can show that with truth tables, right? Or you can show it by arguing using rules of inference and such. Quantifiers are these for all and there exists kind of things. So sometimes we can write propositions that have a variable in them. They're kind of like functions. So let P of X be the proposition X can fly. So P of bird is the proposition that bird can fly. P of whiteboard marker is the proposition that whiteboard marker can fly. Right? It's a family of propositions. And so we can say there exists an X contained in, maybe A is a set of all animals. There exists an X in the set of animals such that P of X is true. So that's exactly what it says. There is an element of that set for which P of X is true. So as long as we consider birds to be animals, right, this is a true proposition. For all X, P of X would say for all animals, that animal can fly, and that is not a true proposition unless you take your cat and put it on an airplane and then your cat's flying. So existential quantifier and universal quantifier. And we're building propositions, right? This is a whole family of propositions. This is another proposition saying there's something in this family of propositions for which this is true. This is saying every proposition in that family is true. I should probably say for all X contained in A. And you can nest quantifiers, and they don't always work the way they intuitively seem like they should. But again, break it up, start from the middle, and just look at it one quantifier at a time. All right, and we talked about fallacies. So we have things like detachment. If P implies Q is true and P is true, then Q is also true. And indirect reasoning, if P implies Q is true and Q is false, then P must be false. And there's versions of those that are not true. If P implies Q and Q, then P, that's a fallacy. Because Because Q might be true just because Q is true, right? Q is the proposition, I'm wearing a coat today. P is the proposition, I won the lottery last night. Well, if I won the lottery last night, I'm definitely going to wear a coat today because I don't want to get a cold when I've got all this money coming to me, right? But even though that's true, and it's true that I'm wearing a coat today, that doesn't mean I won the lottery, right? This has nothing to do with P. So that's a fallacy. And the other fallacy, so that's the fallacy of affirming the conclusion, okay? And then the fallacy of denying the hypothesis says if P, then Q, and if P is false, then Q must be false. And you can use the same example. If I'm won the lottery last night, then I'm wearing a coat today, and I did not win the lottery last night, so I'm not going to wear a coat today. Well, no, I wear a coat every day. So that's denying the hypothesis. All right, so methods of proof, basically direct and indirect. Indirect is usually a proof by contradiction. So state what you're given, work logically from step to step until you prove the thing that you're trying to prove. That's a direct proof. State what you're giving and then assume the negation of what you're trying to prove and argue to an absurdity and therefore conclude that the thing you're trying to prove can't be false, it must be true. That's an indirect proof. Yeah.
How do you start an indirect proof? You start with the negative outcome, or what?
Yeah, so prove if x squared is even, then x is even. So let's start off with x squared is odd, right? And that's an assumption. Sorry. We're trying to prove if P, then Q. So assume the negation of Q. And then prove false. So in this case, it's that if x squared is even, then x is even. So P is the proposition x squared is even. Q is the proposition x is even. So let's start off by assuming x is odd. So that's an assumption. And if we argue that x equals 2n plus 1, x squared equals 2 times something plus 1, we can eventually show x squared is odd. Okay, that's a direct proof. If x is odd, we can show x squared is odd. But we also know x squared is even, because that's our hypothesis. And this is a contradiction, because it can't be both even and odd. We have to state that somewhere. Therefore, x is odd must be false. So not x is odd must be true, which means x is even. So negate the conclusion, argue to an absurdity, and then say, well, I guess the conclusion must be true then. Because if it's false, we get, false equals true. And really what we're doing is we're trying to prove if P, then Q. We're assuming not Q. And we're assuming P. And then we're going to prove eventually that false is true. Right? So what we've shown is not Q implies false. Well, that's equivalent to the contrapositive, which is not false implies not Q, which means true implies Q. And we know that true is always true, and so we know Q is true. So an indirect proof is really the same as a proof by contradiction. And it's really a direct proof of the contrapositive in some way.
But true is always true.
True is always true. But if we can prove false, then we've proven false and true is true. And we know that's false. All right, so go over your proofs, ask questions if you're not sure, but main thing, make sure you're always writing propositions, make sure everything you write is true, either because it's been told to you that it's true, or we're assuming it's true, or it follows logically from things that we've already shown are true. All right, number theory, mostly we talked about divisibility. So, and we had this special symbol, D vertical bar N means D divides N, which is the same as N is divisible by B, by D, or D is a factor of N, or N is a multiple of D. Right, but that vertical bar is not a slash for divide, right? It's a totally different symbol which we can interpret as meaning divides. So the thing on the left divides the thing on the right. It's a bit of an unfortunate notation. And so if we're thinking about integers, we can talk about when one integer is divisible by another, meaning it goes in a whole number of times. And there's this thing called the division algorithm, which basically says if you pick two numbers, like say 27 and 6, I can write 27 equals 0 times 6 plus 27. 27 equals 1 times 6 plus 21. 27 equals 3 times 6 plus 9. 27 equals 4 times 6 plus 3. 5 times 6 plus negative 3. 6 times 6 plus negative 9. And so on. And even though there's different ways we can write this number as a multiple of that plus a remainder, there's exactly one way we can write this, where the remainder is bigger than or equal to 0 and less than the thing we're taking multiples of, 6. So there's always a unique remainder that's, between 0 and n minus 1. That's what the division algorithm tells us. It's a theorem that states that. And so we typically write something like 27 is congruent to 3 modulo 6. It means these two things have the same remainder when you divide by 6. It means their difference is a multiple of 6. And we can just as legitimately write 27 is congruent to 21 modulo 6. Because that is a remainder when we divide 27 by 6, right? 6 goes in once with 21 things left over. But usually we're looking for something between, in this case, 0 and 5. And there's always a unique number like that. So we can take the whole collection of integers all the way up to, however large we want to imagine, and we can reduce it to, in this case, just a simple set of 6 numbers, 0, 1, 2, 3, 4, 5. And say that any number is equivalent, congruent to one of those 6. And once we have that congruence, we can do things on these congruent values and say something about the original values. So we have 27 squared would be congruent to 3 squared modulo 6. Why? Because 27 is congruent to 3. 27 plus 50 should be congruent to 3 plus 50 modulo 6. Why? Because 27 is congruent to 3. And so some of the stuff we did with these congruence relationships and what we looked at cipher systems and so on, we're using this fact that we can reduce modulo 6 either before or after we do these operations. But reducing something modulo n preserves addition and subtraction and multiplication, but not division. So that's what modular arithmetic is. Uniqueness of modular equivalence, the division algorithm, we talked about that. Okay, primes. Primes are numbers divisible only by themselves and 1. 1 is not considered prime, 2 is prime, 3, 5, 7, 11, 13, these are all primes. 9 is not a prime because it's also divisible by 3. There's an infinite number of primes. That's important to know. Pick any number and eventually you'll find a prime bigger than that number. But the primes thin out as you look at larger and larger numbers because there's more stuff that these numbers could be divisible by. The number of primes less than or equal to n is asymptotically equivalent to the natural log of n. Meaning as n gets bigger, this gets closer and closer to that. So the number of primes less than or equal to a skrillion is approximately the natural log of a skrillion. But it's not a very good approximation because a skrillion is really a small number. It's only like a bunch of zeros. But the number of primes less than or equal to a googolplex, which is like, it's either 10 to the 100th or it's 10 raised to the 10 to the 100th. It's going to be pretty close to the natural log of that. So that's the prime number theorem, and that's a cool thing to know. Greatest common denominator, greatest common divisor, sorry, Euclidean algorithm. So this you've done a bunch of times, 63 and 6. So you write 63 equals something times 6 plus something. So 10 times 6 plus 3. And then you bring these down, and 6 equals something times 3 plus something. Well, it's 2 times 3 plus 0. And so this is your GCD, is 3. And you've done questions like that, and you did some on the midterm, and people look solid on that. Modular exponentiation, Fermat's little theorem, these were ways to do larger arithmetic calculations using modular operations. So modular exponentiation, I don't know, let's say you want to compute a to the 27th modulo b. So the idea was, think of 27 as a binary number. So it's 16 plus 8 plus 2 plus 1. Right, which tells us that 27 is equal to 2 to the 0 plus 2 to the 1 plus 2 to the 3 plus 2 to the 4th. And so calculate the powers of a that are themselves powers of 2. So a to the first is congruent to a. Calculate a to the second, a to the fourth, a to the 8th, and a to the 16th. And to do each of these, you just have to square the previous one, right? A squared is, square this and reduce it modulo b, and you'll get something between 0 and b minus 1. Take that result and square it again, that'll give you a to the 4th. Take that result and square it, that'll give you a to the 8th. And the biggest any of these things gets is b minus 1, so the biggest the square gets is b minus 1, so it's relatively small. Even if you carry this out to where you've got, a to the 1024th, right? And then a to the 27th is congruent to a to the a to the first times a squared times a to the 8th times a to the 16th. So take the terms that you calculated that correspond to that and multiply them modulo b, and you're done. And if you keep reducing modulo b, again, you never have to work with anything bigger than b minus 1 squared. So you've done problems like that. We've done problems up here like that. The other trick we talked about was Fermat's Little theorem. And Fermat's Little theorem is basically a to the p minus 1 is congruent to congruent to 1 mod p. As long as the greatest common divisor of a and p is 1.
And from that, you get a to the p is congruent to a.
That gives you a to the p is congruent to a. And it turns out this is always true regardless of whether p is prime or not. But it's actually more powerful to know that a to the p minus 1 is congruent to 1. So if you know a to the p is congruent to 1, that's nice because you can take powers of that and it's just going to be congruent to a power of 1, which is 1. So a to the p minus 1 times anything is going to be congruent to the 1 to the k, which is just 1. So this lets you take giant leaps in finding powers of a. For example, if a to the 10th is congruent to 1 modulo 11, well then I know to the a to the 10, anything is also congruent to 1. Or a to the 7 anything, or a to any multiple of 10 is congruent to 1.
Pretty powerful.
Yeah, ones are nice that way. So we can use that to do large exponentiation. Get close to what you're after with this, and then just multiply up a few more times to get a to whatever power you're actually interested in. All right, applications. I'm not going to ask you about applications, but we can use these things for doing things like parity generation, parity calculations, check digits, UPCs, universal pricing codes, ISBN numbers, stuff like that. And we can use them for cryptography. I don't have cryptography up here, which is okay because there's no crypto questions on the test. But we talked about, different ways to do encryption.
That
I think there's
RSA,
no crypto questions on
that RSA stuff was, to me, one of the most interesting.
Yeah, me
things in the
too.
course. That was really, really interesting, the application of mathematics to come up with a
Yeah.
pretty cool result.
All right, so induction. So there'll definitely be some induction questions on the exam. So induction, the whole drill for induction comes down to the following. Prove, it's a family of propositions, say P of n for all n bigger than or equal to 1. Okay, trying to prove something about an infinite family of propositions, that's fairly daunting. If you can prove the following, prove that a single proposition like P of 1 is true, and prove that if P is true for n, then it's true for n plus 1. Then you can conclude P of n for all n bigger than or equal to 1. So we want to prove that infinite family of propositions is true. We can do it by simply proving two things, a base case and this inductive step, which says if it's true for n, it's true for n plus 1.
So prove the base case, and then essentially do n plus 1 to both sides, and then try and get that to match. Or add whatever n plus 1 would be to both sides.
Yeah, so assume, so to prove this, right, assume P of n, that's your hypothesis, something that eventually lets you show P of n plus 1. So yeah, if this is a proposition about the sum of integers, you assume P of n that shows you the sum of the first n integers, add n plus 1 to both sides, and you know those sides will still be equal because they were equal before you added the same thing. But now take that equality that you've just proven and show that somehow that leads to P of n plus 1.
Right.
In that case, because you can just do algebra and rearrange it to look exactly like P of n plus 1.
Right.
But if it's, you know, people throwing pies at each other, you know, n people have a fight and there's a survivor, and now have n plus 1 people and somehow show that there's still a survivor because there was a survivor in this case, right? And that lets you prove n plus 1.
Would it be possible for you to do an example of this?
Yeah, what kind of example?
How about a simple like equation? I don't know.
Okay.
The steps that go through it on how to prove it.
Sure. Let's see. Oh, I thought I had a good one. Let's see. All right, well, let's just pick on odd integers. So the sum of the odd integers up through 2n minus 1. So this is the first n odd integers. Prove that the sum of the first n odd integers is n squared. So state a proposition. Okay, it's a proposition about n. P of 1 says that the sum of the first odd integer is 1 squared. P of 5 says the sum of the first 5 odd integers is equal to 5 squared. So P of 1 is true, because it says if you take one odd integer and add it, you get 1 squared, which is what 1 is. So prove P of n implies P of n plus 1 for all n bigger than or equal to 1.
So the real deal is what you just said earlier. P of n is not just one proposition. P of n is a whole family of propositions.
Mm-hmm.
Whereas, and that's the essence about mathematical induction is when we assumed that n is arbitrary and proved the nth case. The nth case implies the n plus 1 case.
Yeah,
Proving that for every n.
right, yeah, what we're really proving is prove P of n for all n bigger than or equal to 1. Right, P of n is just one proposition, whatever the value of n is. But this original question is really asking us to prove a stronger proposition, which is for all n bigger than or equal to 1, P of n is true. Right? So we're trying to prove an infinite number of propositions are true. Okay, so we want to prove P of n implies P of n plus 1, so step 1, P of n, because that's our hypothesis. Step 2, what does P of n say? 1 plus 3 plus 2n minus 1 equals n squared. That's the definition of P of n. And I'm just going to add 2n plus 1 to both sides. So I had an equality, I added the same thing to both sides, it's still an equality. And then I'm going to factor 2n plus 1 plus n squared to be n plus 1 squared. That's just more algebra. And I'm going to notice that if this is what P of n says, P of n plus 1 says 1 plus 3 plus da-da-da plus 2 times n plus 1 minus 1, which is 2n plus 1, should be equal to n plus 1 squared. So I've proven P of n plus 1. That's the definition of P of n plus 1. And so by assuming P of n, I've proven P of n plus 1, so this implication that I just wrote in step 6 is true, right? And then step 7 is P of n for all n bigger than or equal to 1, and that's due to mathematical induction plus, step 0, which was our base case. And that's what we were asked to show.
So you're not allowed to say P of n plus 1,
Right.
like step 3. for example.
Right, exactly, yeah.
So you just have to get it in the form where it would obviously follow that.
Yes,
P of n
exactly.
plus 1 would look like that.
Mm-hmm. Right. And it's very subtle sometimes, right? I mean, this is almost exactly what P of n plus 1 says, right? But I didn't write it because Pn plus 1 is true. I wrote it because step 2 was true and I added something to both sides. So pretty much every mathematical induction proof looks basically like that. You have something you're trying to show for all n. You make a proposition, you prove that proposition for some base case value, and then you construct a proof showing that if that proposition is true for n, it's true for typically n plus 1. And you do whatever you have to do to make that proof come out, and then you can throw mathematical induction as your reason and say P of n is true for all n. And it doesn't have to start from 1, it could start from 0, it could start from 50, right? As long as you show the corresponding base case, right? And we could do, P of n implies P of n plus 2 if we only cared about odd numbers. We could start from 1 and show if it's true for n, it's true for n plus 2. That would prove a proposition about odd numbers. But the basic style of this, the feeling of it is the same. All right, recursive functions we talked about in the beginning. Pigeonhole principle, so this is about counting problems, right? So n objects and n minus 1 containers. If you put each object into a container, there's at least one container with at least 2 things in it. That's the pigeonhole principle. But we use that to argue all sorts of things like if there's only 5 classrooms in a building and there's 7 classes that need to meet at the same time, at least one classroom is going to have 2 or more classes scheduled to meet in it. Because your pigeonholes are the classrooms and the objects are the classes, and if you start putting classes into classrooms and there's only 5 rooms and there's 7 classes, there's going to be at least a doubling up in at least one room. And it could be that all 7 classes get scheduled for the same room, and you have one room with 7 classes and you have 4 rooms that are empty. That's okay. But you're guaranteed that somewhere there's at least one room with at least 2 classes scheduled for it. So it's a counting argument, and we looked at a number of applications of that. Product rule, sum rule, principal, inclusion, exclusion. This was your last homework, right, which we talked about on Monday. Taking a task and breaking it into a series of tasks in succession, that's the product rule. Breaking it into a series of tasks that we can choose from, that's the sum rule. And then inclusion, exclusion is this idea that if you take a union of 2 sets, you end up with possibly fewer things than the sum of the number of things in each set. Because if there's things in both sets, they only appear in the union once. And we saw some problems related to that. And then generally permutations come out of the product rule and they apply to ordered collections of things. So if you want to choose objects in a particular order, right, you can break that into a set of tasks. Choose the first item, choose the second item, choose the third item. And if you have n items to pick from, you can choose the first item n ways, second n minus 1, third n minus 2. And the number of ways to complete that task would be n times n minus 1 times n minus 2. And that generalized into this handy formula for the number of r permutations of n objects. Turns out to be n factorial over n minus r factorial, which is really just n times n minus 1 times n minus 2, a total of r times. So that's when that's when the order makes a difference. If the order does not make a difference, then we're talking about something called combinations, which is the same as permutations, but divided by r factorial, the number of arrangements. So this is n factorial over n minus r factorial times r factorial. And we often write this as just an n on top of an r in parentheses, but without a line dividing them. So it's n choose r.
Could you state the product rule and the sum rule the way you said it before?
The way I said it just now?
Yeah, just now.
Okay.
It was a little,
So if you have a task that can be broken down into a series of subtasks that have to be performed in succession, then the product rule applies. And the number of ways to do the original task is the product of the number of ways to do each subtask.
Oh, does that tie into like Big O?
Not directly. I don't
I'm
think
sorry,
so.
what did you say?
Oh, like figuring out how long the program takes to do something, essentially.
Oh, okay.
Yeah, so there's this whole complexity theory about algorithms. If we wanted to do a more exact calculation of Big O, this would start to come in, right? But usually Big O, we're using really broad brush strokes and trying to find very approximate, and so a lot of details get brushed away.
Are you saying the product rule would come in? Or are you talking about that?
Combinations in general
Oh, okay.
and permutations.
And then how did you state the sum rule?
So the sum rule is when you're trying to perform a task, and you have a choice of subtasks that you can perform. Then the number of ways to do the whole task is the sum of the number of ways to do each subtask. All right, Pascal's triangle is just this cool little triangle. Starts with a 1, has 1s on the diagonals, and each entry is the sum of the two things above it on either side, and your 1's going down the edges. And this actually looks like this. So each entry is just a combination. And nth row R column, the entry is just the number of R combinations of n objects. And we get cool things out of that. Binomial theorem, you had a homework problem on, but it basically, it's another way to use combinations to look at binomial expansions. And I will not ask you about this on the test, but you know, a plus b to the n is equal to n a to the n, b to the 0, plus n minus 1, a to the n minus 1, b to the 1, plus n1, a to the 1, b to the n minus 1, plus n0, a to the 0, b to the n. So we know if we take a plus b to the n, we get a bunch of these, you know, a to something, b to something, right? And if it's a cubed, it's going to be b to the n minus 3. The sum of the powers is always n. And there's coefficients in front. Well, those coefficients just come out of formula for combinations. Or you can read them off Pascal's triangle. So that's the binomial theorem, binomial expansion. And then grammars and languages, none of that will be on the exam. But we basically talked about phrase structure grammars, right? A formal way of describing a language that lets us have a set of symbols, a collection of terminal symbols, a start symbol, and a set of production rules that let us change one symbol into another, or one string into another. And starting from the start symbol, any word that we can derive comprised of terminal symbols is part of the language. It's a sentence over that grammar. Talked about finite state machines, a little bit with state diagrams, using state machines to recognize strings. And we talked about Turing machines as an example of a finite state machine. And analyze some programs and put together some programs for that. We talked about classes of problems, so P and NP complete, and the possibility that some NP complete problem will be solved, in which case all NP complete problems are solvable in polynomial time on a plain old Turing machine. We talked about limits of computation and the halting problem in particular. And so there are some problems for which algorithms do not exist for their solution, apparently.
So, study grammars and languages, or what course?
So, if you go WSU, for example, there's a course on automata theory. I think you normally take it your junior year. And that, picks up where this leaves off.
I've heard of it that like modern AI is essentially just a really intricate state machine.
Yeah, yeah.
Right?
I mean, it's possible the universe is. And all of our computers are really glorified state machines. It's a pretty powerful way to look at things.
How did, now, there's, this, I'm just talking about things that I've heard about, but I don't know really about regular languages and natural languages.
Mhm.
How does that fit in here?
So natural language I usually think of as meaning like spoken language, right? So a natural language processor is like something that tries to understand English, for example. And that's, very much a machine learning kind of topic. Regular languages are usually looking at grammars such as we did. And there's different types of grammars, there's classes of grammars.
Again, would those regular languages be studied?
Yeah, that's automata theory stuff.
Automata
Yeah.
theory, okay.
Roughly how many questions are going to be on the final exam?
Roughly 8 questions worth roughly 12 points each, with 4 points for your name. So I've told you one of the questions already.
It's on Monday. Noon.
It's on Monday at noon, yeah,
In here.
in here.
What would be some recommended formulas to study? I'm assuming the page 58, the laws or rules.
Yeah, so bring those with you, right?
Mhm.
And you get 8 pages of notes outside of that, so that's bonus pages. Yeah, so do some problems that do this kind of modular stuff, modular exponentiation using Fermat's little theorem. There's examples in the book, there's homework questions, so there's a few alternative textbooks posted on Canvas. The main textbook doesn't go into number theory the way that we did, but some of the other texts do. So you can find problems to work on with that, and examples in the chapters. Definitely work on some proofs, but those are a little harder to do because, modular exponentiation, you can do the problem and you get the answer and it's 16 and you can see if that's correct. A proof, you can write it up, but you can't look in the back of the book and see if I did the proof right because there's different ways to do it. But if you feel like you're doing it right, you're probably doing it right. If you feel like I have no idea if this is right or not, then, let me know. Go over the Euclidean algorithm for greatest common divisor, so you're comfortable with that. Definitely product rule, sum rule, those kind of homework questions that we did for the last homework, those are all different formulas, combinations, permutations, right? Play with those formulas, be comfortable with those. But pretty much everybody seemed to have the right choice of is this a permutation, is this a combination, right? People seem to be doing better than the usual case on those from past classes, so that's always good.
Would you say the exam kind of prefers more recent material?
I think it's got more on the recent material than on the older material. So, yeah.
Do you, how do I say this? Do you say that we can have 4 8x10 pages of notes?
Any size you want, and you can write as small as you like, and I know what this means for you, because I've seen your writing.
So actually,
And as many colors as you like.
Well, I feel that is kind of a statement or a comment you're making on certain specific individual teachers who require students to have one 3x5 or one 4x6. I mean, the point is that if you actually do it, if you actually do a card or a page or 4
Mhm.
pages, you're probably not gonna use it on the
Right,
test
right.
anyway, but just doing it
Yes, yes.
helps you summarize, review,
Mm-hmm, sure, sure.
but it's.
But
a
if you
way-
try to write 100 pages as part of your plan for studying, that's not gonna work any better than actually having 100 pages on test day. So my feeling on this course and 224, you know, the programming sequence, CS sequence, is that I don't want you to be hindered by your memory or by not having access to your textbook, right? So I pick, you know, 4 double-sided pages because I believe that's going to be enough for everybody. If I don't do that, if I say open book, open note, in the past I've had people come in with, you know, a printed copy of a 1,000-page Java manual and their notebook, which is on 3 different binders, and the whole exam, they're just like flipping through, looking for the answers, right? And you're never gonna find them in there. So the page limit is really just to say, you know, like learn the stuff, practice the stuff, be familiar with the stuff so that you can produce it from your head on the exam. But, you know, if you can't remember the syntax for this statement, or you can't remember what the Euclidean algorithm says or something, right? Put it down on a piece of paper and don't stress over it. So I want you to have, you know, a page budget. So if somebody really feels like they want 11 by 17 pieces of paper, I'm not gonna kick them out of the test for that, right? And you see videos sometimes where someone comes in and they unfold, you know, this like life-size map of Britain or something, size paper filled with notes, and, you
Well,
know.
They've also, I've heard, you could write it in a certain pen where you can see.
Oh, from
black
different
underneath,
angles?
Red underneath and black on the top.
Oh, yeah,
So you're using the same space to write.
right.
Like
That would be cool.
multi-dimensional
Yeah.
page.
You can do a similar effect with the blue and red
Yes.
3D glasses.
Right.
You just close an eye.
Totally. And if you don't specify the thickness, you could use a piece of paper that's that thick.
Are you the one teaching the next course in the sequence?
222?
Mhm.
Yeah,
Okay, cool.
yeah. Yeah, so I'll be teaching 222 and 223.
What, next term?
Yeah, 222 in winter, 223, which is Java in spring. 224 in fall. All right, I think everybody's in good shape here. Thank you for your attention and energy in this course. I think it was a fun course for me. Hopefully you got good stuff. I will see you for your exam for sure.
All right. Thank you, Nick.
Yep.